Hello and welcome back to Calculus 3. We are continuing our exploration of integrals, and now we are going to talk about triple integrals, because we figured out that anytime when we have a subtraction of two functions, we can put that as the limits of another integral, leaving the space for yet another dimension of a function to be integrated, meaning, right, raising the stakes. So earlier, in the last lecture, we dealt with the shape, which we are not going to compute again, but we dealt with a shape like this, right, which is elliptical paraboloid, and we said that the volume for this was set out to be a double integral, and then we had -3 to 3 on the x-axis. Then we have negative square root of 9 minus x squared and positive square root of 9 minus x squared. And here is the important part. We had 9 minus x squared plus y squared, which is the shape. So top of the shape minus bottom of the shape, and then we had dy dx. Now remember what we said before. When you have these two functions subtracting, you can actually put those in limits of the yet another integral that you can nest inside. So now this actually could be written as well as triple integral. So you have your -3, your negative square root of 9 minus x squared, and then the bottom one over here would be x squared plus y squared. The top would be 3, positive square root of 9 minus x squared, and it would be 9. So what I can do is I can place these guys in the limits, and then just have the dz, dy, dx. So the inner integral now would be the z integral, and that is what is new for now triple integration. Now, we don't have any function in here. That means that we only have 1, 2, 3 dimensions, and we are calculating volume. However, having a triple integral gives us opportunity to put something in here, which would be the fourth dimension. Now, why would we have a fourth dimension? Well, the 3D objects that you can pick up and you know, look at have density, and they have temperature, and have all these other attributes that you can you know, assign to that object that you can hold. So the triple integral would be sufficient to describe in full the three-dimensional object that you can pick up, and then you can integrate whatever other concept you want to have within those integrals. The solution, right, the solving of these is going to be, again, the inner first, and then the outer, and then all the way at the out, right? So you, again, layers of the onion, right? You start in the middle, and then you go out. If you had 15 integrals, or you know, on a pile, you will still do the inner first, and then go out one by one. So now this, again, just gives us another layer. The triple integrals could be 3D for volume, or 4D, right? And they can be either rectangular, or they can be general regions. And then the next lecture, we are going to do the triple integrals that are upgraded polar coordinates. So now we're covering rectangular version. And then when we move to the next one, we are going to take a look at cylindrical and spherical ones. So that's a separate lecture. Now, the integral for today is going to say that the triple integral over region V of f of x, y, and z dv could be, and now we have to, I'll give some space over there. So f of x, y, and z, and now I'm going to put dz, dy, dx. Again, the problem the problem will determine which order you're going to have these in. This is a standard order, dz, dy, dx. That's the most standard, the most frequent one. However, it's not the only one. It could be, any other way. To change the order of integration there is a living nightmare, right? Because we've seen that it's not easy to change the order. Even for double integral, you have to draw the region, then you have to redefine all of the variables and all of that kind of stuff, and then put the other one together. So this is going to be that much harder to switch. Unless it's a rectangular, which means just numbers. In that case, it's easy. You can swap them in any way you want. So now, what do I have? Well, the x is the outer, so these are my a and b. Now the next one is y. Remember that the y is a function of x. So this is going to be g of x and h of x. Those are my functions, right? And then you have z. Now z is the function of x and a y. So this is going to be capital G, xy, and lowercase, uppercase h of xy. So this is the general region. This is the triple integral. This is what we are focusing on. And you guys will be looking at the shape and setting up the integral using this definition. Now, clearly, if you switch, your dv could be dz, dy, dx, or dz, dx, dy, or, right? And I'll put 3 dots because you have how many combinations? Very good. You have 6, right? So now, could be any one of those. You used to deal with representative rectangle, which in double integrals we changed into a representative French fry because you had a little delta x, delta y in the base, little square or rectangle, and then there was a representative French fry on top of that, right? Now you are dealing with the representative cubes, representative ice cubes. So actually there is a very good graphics in a book. So let's take a look at that graphic so we don't have to worry too much about drawing this thing because it gets to be a little bit involved. If you take a look and you are going to cut delta x, delta y, delta z because you have dx, dy, dz, right? So you are going to take your 3D space and you are going to partition that 3D space. Now, is there a way to picture this? Well, if you haven't played the 3D Tetris, I'm sorry, it's going to be a little bit tougher. But in my case, I don't know. I look at this room, and I look at that wall over there, and I see all of the rectangle grid, and I see the rectangle grid over there, and I see the rectangle grid on top. So now I just let that grid go this way, and let that grid go this way, and let this grid fall down, and then they all intersect into rectangles all over the place. So now, what are you? You are just an amazing resolution of all of these rectangles around. That's what you are. Think about the pixels, right? The smaller the pixel and the more pixels you have, the better resolution it is. Right? The people see a lot of people have no clue thinking about, oh, my camera is 12.1, megapixel, and I say, really, what's a DPI? Because DPI is crap. Your camera is crap. I don't care what your how many megapixels it has, because it's not a representative. DPI is representative, dots per inch, right? Because if you have 12.1 million pixels and each pixel is as big as my head, you have the greatest camera known to man. All right. So dots per inch you are trying to make. This is why that these cell phone screens are so insanely well made and good, because they have those pixels so small. You can have a large resolution on a very small device. Those screens are far better than any TV screen or computer screen you've ever seen, because the DPI for the cell phone screen is insane, right? So that's this kind of deal. What you have is any object that you have, anything that you pick up, right, is constructed from what? Atoms, right? That is your ultimate pixelation right there, right? Well, molecules, but atoms eventually, right? So that's why this is such a good resolution, right? You can't even see those pixels and how small they are, right? And it's proven that we will never be able to observe them directly, obviously, because they are smaller than the wavelength that we can see, right? If you don't know that, well, let's take a look at the measurements between 10 to the negative 9 and 10 to the negative 15. It should be immediately clear that we can see. It will never be able to see unless we evolve even more to see better wavelengths. Now, whatever creature is able to see the wavelengths of negative 15, then we can ask them to describe what the atom would look like. So there's no amplification that you can do with the microscope and whatever that will fix that. Anyway, going on back to this. So you have your delta x, your delta y, delta z. You have a representative ice cube sitting in the middle. And now what we have is, well, we just have integral for each one of those dimensions. And as you make each one of these dimensions as small as possible, right, sending the number of rectangles or these ice cubes to infinity, you are getting ever increasing resolution, right? So less and less error, and then it will compute the exact volume when you have infinitely many of these ice cubes stacked, and they make a contour of the object that you are observing, right, and lifting exactly. So going back to our formula, now we are going to work out the integration the same as before. You anchor the one at the end. There we go. So this is your anchor, right? And then you go inner and then inner. So the same situation like you had for the double integrals. The first example obviously would be just the integration of the calculating the volume of the box. So if I have, I know, give me 2 more minutes and we're done. If I have a box like this, so we have a box, and this box sits in a coordinate system. X, Y, and Z. Should be sitting in front, but that's okay. And I'm going to say that, well, this is obviously origin 0, 0, 0. Let's go on Y direction. Let's say the Y direction is going to be, that's a 6. Z direction is going 3. And let's say the X is going -2. We can find the volume of this box. The first thing that I'm going to do is I'm going to draw the domain. Domain has, it's 6 on Y, and then a -x. Okay, there we go. So we have 1, 2, 3, 4, 5, 6, and then -2. So -2 and 6, this is Y, this is X. as I am setting up the volume integral, I am not going to have any function. I'm going to say standard is z dy dx. And now I see that delta x is the delta x is the anchor over here. So delta x is between a -2 and 0. That's delta x. Then I have the bottom of that delta x is on the x-axis, which is y is 0 there. And the top is writing y equals to 6. So that's that. And then when I go back to the object, I see that the bottom of this shape is sitting on the xy plane. So that's, I'll put the red 0 here because I want to put the arrow and say xy plane. And the top is 3 because of the z equals 3 plane, which is the top. So all of these are just bounds that completely bound the object, right, and make it finite. So you have the planes, -2 and 0 on sides, then you have 0 and 6 on the other two sides, and then you have 0 and 3 on the third pair of sides, and that cuts off the box. Now, clearly, the area of this better be, the volume of this better be 36, right, because 2 times 3 times 6, that's 6 times 6, 36 units cubed. So when we compute this integral, we better get 36. So as I integrate, oh no, that was a sneeze. So good effort. We have integral of 1 in terms of dz, so that's just z from 0 to 3. We still have dy and dx to deal with. By the way, these just take forever because there are 3 of them, obviously. And then when you get, partial fraction decomposition on one leading into the trig sub in the next one, obviously is going to take time. No? All right. So this is 3 dy dz. So the next integral is in terms of y, so we get 3y from 0 to 6. We still have dx. Make sure you're copying these every time. So this is integral -2 to 0 of 18 dx, which is now 18x computed from -2 to 0. When you plug in 0, you get 0 minus 18 times -2, and there's your 36, right? So next time you're tutoring a kid and they go, why? For the volume of the box, there you go. Now it's clear, right? Obvious, easy, trivial. That's another, right? That's another good word to use. Why? It's trivial. Don't worry about it. But we clearly didn't gather here in such a large numbers to calculate the volume of the box, right? We would like to see something that is more involved and more interesting. So let's take a look at a shape from homework and figure out what would be a good way to set that thing up and work. So as you can see, finally we have more than 4 problems to enjoy. If you take a look at this, first 14 problems are just mundane calculations on, can you integrate 3 times in one problem? But then when you flip problems 15 to 24, look at that. You get all these wonderful shapes that you get to consider and solve. And solving some of these is easy and nice, and solving some of these should be a living nightmare, like problem 17, for instance, because problem 17 is supposed to be spherical integrals, which means that solving it this way would warrant some of the calculations that you might not want to do, like I did previously, right, with calculating the polar integral using rectangular coordinates, which is not a right idea. So when you have enough knowledge, you will immediately see the shape, what it looks like, and then you will decide whether it's rectangular, cylindrical, or spherical. So now we're just stuck with rectangular. So we can set up all of these and possibly not compute. Let's take a look at some of the basics. So let's go 15, 16, and maybe 20. 15, 16, 20. Sounds good. I will not be integrating because I don't want to waste time on Calculus 1 basic integrals. Technically 90% of your skill here should be being able to set this thing up. So I'm going to copy the picture first, and then I'll switch the screen. So we go from 6 to a 4 to a 2. So the first problem here has us do this. Now, you see that the book is basic. They actually give you the equation of this plane. As I've said, I will never insult you that way, because you have the 3 points, you can set the 3 vectors, you can come up with the equation of the plane like this, right? Because you know how to find the plane when you have 3 points, and you do have 3 points. 6, 0, 0, 0, 4, 0, and 0, 0, 2 are 3 points that are given to you. So setting up vectors and figuring out the cross product for a normal vector and coming up with the equation. Equation is 2x plus 3y plus 6z equals to 12. So that is the equation of the plane. Now this is some kind of a triangular wedge, something, whatever it is, right? This is a solid 3D piece, right? This is the back end. This part sits on the floor. So it's what it is. So now, what way are we going to deal with this? Well, guys, if you really want to learn and know how to do these things, listen. Right? Listen. And in this case, the part of the listen is draw the domain on a side every time. Draw the domain, because that will help you figure things out. The domain is going to be your good old xy. You are used to the xy. You know what it is. You know how to work with it. So x goes 6 units out. 1, 2, 3, 4, 5, 6. And y goes 4 units up. You have this triangle over here. When you have this triangle, guys, you draw your dx, and you immediately see everything you need to see. You see your 0 to 6x limits. You see your 0 to a function y limits. And then you will have your z equals 0 for the bottom and z equals the plane on the top. So it is very straightforward in way you set these things up. But if you don't draw this, you will be struggling with limits of integration. So here we go. I'm going to now start this volume integral and say I have a triple integral here. I have nothing inside. I'll go dz, dy, dx. And now, since dx is in my anchor, I have 0 to 6 on the outer limits. And now I have 0 to the top of this is sitting on this linear line. A linear line is y equals negative slope. Rise over run, that's 4 over 6, which is 2/3. X plus the y-intercept is 4. So your limit, upper limit, is negative 2/3 x plus 4. And there is no way to get that anywhere else. All right, you're looking at this thing, and you draw the domain. Domain is the floor on which the object sits. So I see the triangle on the floor over here, and I see that x goes to 6 and y goes to 4. So x goes to 6, y goes to 4. And that gives me this line. And now I know algebra. Obviously, if you don't know how to write the equation of the line, then don't sit in Calc 3. But you can easily come up with this if you draw the domain on a side. So one more time, our y was the slope. Slope is negative because it goes down. Rise is 4, run is 6, so 4 over 6, that's 2/3. X plus the y-intercept at 4. So I have that, and now for the z limits, I have 0 because z equals 0 floor. And I now have the top. Now the top is going to be our equation that is solved for z. So now I have to take this equation of the plane and I have to say 6z is equal to 12 minus 2x minus 3y. Divide by 6 everywhere. Z is equal to 2 minus 1/3 x minus 1/2 y. And this is my upper limit. So 2 minus 1/3 x minus 1/2 y. So now the entire object is bounded. As you can see, it has you draw the domain. The domain is always the fattest your object can get, right? Because you shine the light on the top. It's the shadow that is on the floor. It doesn't have to be the floor, right? The fattest part of me is not touching the floor, right? But the shadow of me will show the big ellipse on the floor to which we have the equation to give me the bounds for these. And then 0 for the flat feet, and then whatever the formula is to come up with this top over here goes like that. All right? So the fattest the object can get is what determines your domain x and a y. Right here, the fattest part. Right here, the fattest part. Over here is the bottom. The fattest part of this is the triangle on the bottom. This is the next problem. This one, parabola, that's also going to be done. That's the same thing above. Right over here we have the rectangle. But this is the ramp. So you guys have to figure out what is the fattest part of the problem, and that is going to give you the region. And then you just take a look, the bottom for z and the top for z, they go top and the bottom of the limits, and you are done. So now the integral is set, so just compute, right? So I'm just gonna say over here equals, and I'm gonna Nike that for you so you can go home and enjoy that calculation. The next object, the next problem is problem 16. Again, just a setup. You should be able to integrate Calc 1 3 times in a row. We have the coordinate system. X, Y, Z. We are going to have a triangular region in the domain. Which has the shape to it. They give you the points pi pi 0, 0 pi 0, clearly the origin 0 0 0, and they tell you that the surface over here is z equals sine x, and they tell you that the this side over here is y equals x, which I know. They don't have to give me this. Look. Pi pi. X is pi, y is pi. They're the same. So x equals y. But anyway. You have to be observant. Domain. Domain is, we have to be careful with the domain. We know we have to draw a 45-degree line. So 45-degree line. Say this is pi over here. So if that's pi, then 1, 2, 3, 4, this is pi as well. And now I get to go either here or here. Well, so let me shade my triangle. Which axis is it touching on the shape? Is it touching the x-axis or a y-axis? Y. So it's right here. You know, be detectives a little bit. It's not arbitrary. So there's your region. And you want your delta x to anchor? Fine. Volume is triple integral dz, dy, dx, because I am not going to use the... So dz, dy, dx, I'm not putting anything inside because I'm looking for volume. Okay, dx, well, clearly from 0 to pi, because the most left delta x can be is at x equals 0, and the most to the right is, right? Now the bottom is touching the function y equals x, and the top is elevation of pi. So this is y equals x, and this is y equals pi. That's the top. And finally I have my blues. Since this is resting flat on the surface, the bottom is 0 and the top is given as sine x. Equals to, boom, just do it. So you will compute this thing on your own, because you are integrating z, which is 1, and then you get your sine x, and then you integrate that, you get negative cosine when you plug in pi and x, right? So you will go to that, and you will compute the values. It's very simple to integrate. As you can see, it's not that hard to set this up. Let's do one more, and then call it a day. Obviously, we're going to review this tomorrow, hopefully do 2 or more examples, and then open the gates of hell, I guess. That's a promise. Just make sure you don't miss tomorrow. So now, I'm going to draw the same. I'm working on a problem 20. So now what I have is a parabola around y, and then I have the shape rise up in triangular fashion up. There we go. So that's the shape. And if I draw the domain, domain is good old parabola. Ooh, sine of y, thank you. Okay, sine y, yes. Thank you. Great. All right, so back to problem 20. The wedge bounded by the parabolic cylinder y equal x squared, well, we know that. Z equals, so that's the top, 3 minus y and z equals 0, which is the floor. Clearly, right? So I don't know how tall this is. Oops, I thought I switched. So I have my domain on the side. It's a parabola that it's hugging the y-axis, right? And the only question that I have, the rest is easy to set up, right? I can do everything. The only thing I don't know is what is the height of that. Is it 1, 2, 3, 5, 9, 16? What is the value for y? Because when I draw my representative dx over here, right, to put my integrals together, dz, dy, dx, next class we are going to do different orders of this. See, I don't have these corners here, so I don't know where they fall for my x1 and x2 for this. I know that the bottom for the dy, the bottom is x squared, but I don't know the top. And for z, that's easy, that's given to me. Right? So these are the ones that I know, and these are the ones that I'm missing, and I will figure them out as soon as I figure out what is the value that goes up there. Now there is a way to figure it out. If you note, the line over here, the blue line, is the blue line here. All right, that's the same line. And that line happens on the floor, where z is equal to 0. So if I equal these two equations, z equals 3 minus y, and z equals 0, I get 0 equals 3 minus y, y is equal to 3. I find that that's 3. As soon as I have that as a 3, everything else immediately opens up. So the top is 3. That's going to be my red 3 for this. And the black limits for x better be negative root 3 and positive root 3. Because it's the square root, right? If your y is 3 and your 3 is equal to x squared, then plus minus root 3 is the... Now, this is one of the rare cases where you can exploit symmetry because this shape is symmetric. You see, if you cut this shape on the y-axis, the left side and the right side are the same. So you could go 0 to root 3 and double everything. But I did ask you already not to do that, because if this was cut in any other way on the top, it will not be symmetric and it will be a problem. So, you know, if you believe you're advanced enough and you think you can, you know, safely play with fire, you know, symmetry is something that you can look into. But I've seen it fail more times than, you know, than succeed. So be careful. Be careful with those things. That's that. I will see you all tomorrow, and I'll do my best to bring the merchandise, right? See you tomorrow.